Welcome to your future. Welcome to Vision Academy. Let us unlock your full potential.
A smooth sheet of iron, when exposed to the air, begins blistering and expanding into a layer of rough rust. While they appear unrelated, the rusting of metal, the heat of a fire, biological respiration, and the tarnishing of silver all share the same chemical classification, oxidation. For students, identifying this process often involves navigating a dense collection of seemingly disconnected rules found in standard textbooks. Foundations in chemistry are built on 5 specific definitions: the addition of oxygen, the removal of hydrogen, the addition of a negative ion, the loss of electrons, and an increase in the oxidation state. These 5 perspectives describe a single subatomic transition occurring at different scales of complexity. Historically, oxidation was defined by its most literal observation, the physical addition of oxygen to a substance. This definition was later expanded to include reactions where hydrogen is physically expelled from a compound. A classic displacement reaction provides a clear view of this historical framework in practice. In this interaction, zinc is introduced to sulfuric acid. The zinc atom displaces the hydrogen, breaking its existing bond and forcing it out. In the final state, zinc bonds with the oxygen-rich sulfate group. By attaching to oxygen and removing hydrogen, zinc is oxidized. However, this macro-level shuffling of elements fails to explain the underlying attraction and repulsion that drives the bond. To understand the mechanism, we must look past the elemental symbols and track the charge dynamics between atoms. We can analyze this through a simple combustion reaction, the combination of calcium and oxygen gas. Oxygen is highly electronegative, acting as a magnet for negative charge. When the bond forms, the oxygen's intense charge field completely encompasses the calcium. Because this shift remains consistent regardless of the atom, the rule expands. Bonding with any electronegative entity is oxidation. The rule of add in oxygen identifies a specific instance of a broader mechanism, the introduction of a negative charge field. We can now strip away the molecules entirely to focus on the movement of subatomic particles. Here are the valence shells of sodium and chlorine. We track net charge using the oxidation number, initially 0. As they bond, an electron detaches from sodium and transfers to chlorine. Since electrons are negative, losing one increases sodium's oxidation number to class 1. This mechanism of electron loss is the same whether an atom is becoming an ion for the first time or moving between higher charge states. An increase in oxidation state, the loss of electrons, functions as the underlying mechanism for each of the textbook definitions. Within a closed system, an electron cannot simply disappear. If one atom loses an electron, another must consume it. The gain of this electron is defined as reduction, the exact inverse of oxidation. This interaction reveals the action each atom forces upon its partner. Chlorine is the oxidizing agent, forcing sodium to oxidize by extracting its electron. Sodium is the reducing agent, providing the electron chlorine requires to reduce its own oxidation state. Chemical agents are defined by the reaction they cause in the system, rather than the state they experience themselves. With this model, we can return to the macroscopic examples, such as the tarnishing of silver. Beneath the blackened surface of tarnished silver is a 3D lattice of atoms. Atmospheric particles colliding with this surface physically strip electrons away. As these electrons are removed, the oxidation state of the silver atoms increments upward, resulting in the visible degradation of the metal. Whether it is hemoglobin processing oxygen in the blood or an iron beam rusting in a bridge, every instance is driven by the same transfer of electrons. By tracking the flow of electrons instead of memorizing macro rules, the diverse phenomena of redox chemistry consolidate into a single cohesive framework.
Like this video? Subscribe to our channel. Share this video. Thank you. Shukriya.